can you see the screen? You can see the screen.
Yes, yes, Professor.
Okay, great. Yeah, I think this is slides, right? Yeah, last night we were at here, right? Now let's take a look at this, okay? If you look at this on the left side, you have what? If you look at left side, you have band gap. You see the p-type is amorphous silicon, okay? Look at the materials. Now we have amorphous silicon on the left side. On the right side, have crystalline silicon, okay? So both of these are silicon, but since amorphous silicon has bigger band gap than the crystalline silicon, right? Crystalline silicon, the band gap about 1.12. The amorphous silicon that can be what? 1.8. You see the band gap are different, right? You see the band gap? Band gap are different, okay? So since this band gap are different, we know they were form a heterojunction, okay? They were form heterojunction. Okay, now let's see how this junction is formed, okay? If you look at here, the N-type, the amorphous silicon, right? So amorphous silicon here, the EF is here, look, right? Then the P side is crystalline silicon, P-type dope, okay? That what you see here, okay, is this, okay? So maybe first thing I would show you would be how to plot this, okay? How plot the band bandit there, okay? And then we'll come back to this slides, okay? Now let me just start a new slides here. Then let me copy this so that I copy this to here. Okay. Then I'm going to plot it. Okay, I'm going to plot the after Fourier junction. What that will look like. Okay. So you see there the Feynman is here, right? This is the Feynman, this is the Feynman. I'm going to plot the left side is the same. Left side is the same, right? And then left side I have the same. I have EC, EF, EF. Okay, EF. I have EV. Okay. On the right side, since the Feynman will be aligned with each other, right? With that, I probably should take this up. Right, the better EF because that's important. Okay, this EF is of what on N side, right? On N side, okay, that's the M. This is the P, okay, and then on the right side, this state will be get aligned with this, right? That will be EF1, FP. This is amorphous silicon. This is crystalline silicon, okay, crystalline silicon. Now, far away from the junctions, right? The EV stays the same, right? The EV stays the same here. That's the EV will be the same, okay? My EV. And then far away from the junction, my EC is the same. See the distance here, that's the same distance, okay? Same distance, okay? EC, okay? This is a crystalline silicon, okay? And then you see, the film never is a 9, okay? Okay. Now, the only thing you would like to see, now let's assume, my interface. I'm going to assume my interface is here, My interface is just halfway. See here. This is my interface, okay? This is my interface. And then you see what happens here. Initially, if you think about, if there's no, see here, low offset, see the offset. There's no offset, delta C, delta EC, low offset, delta what? Delta EV. Okay. And then this should be what? This should be something like this, right? Something like this. See that? Something like this. Now, since there's what? There's a delta EC there, right? Which one is higher? That EC on the left side is higher than the EC on the right side, right? That's why I would draw here, with red now. Okay. Now this one, look at here. Okay. Red, I don't know what. This delta EC, right? And then which one is the top? The left side is on the top. So you like this to there, like this to there. Okay. Okay. And then on the bottom, which one is lower? The left side is lower, right? So the left side is lower, right? The interface there, left side is lower, is here. Then the right side is what? The right side is higher, right? Right side is higher, is that. That's what, see here? That's what, delta EV, right? Delta EV. So you like this there, this there, okay? Now you see as what? Okay, I'm going to remove that things there, okay? That so it makes it easier for you to read, okay? Get rid of that. Now, that's what you see your junction look like, okay? You see there's offset in here, there's offset here, okay? This is how you plot it, right? Now, what you see here, is exactly what you see on this side. You see here, the junction, inside the junction, right? This one tiered up, this tiered down, and this one is pushed down because delta EV is that, this delta what? Delta EC, delta EC, okay? That's how you plot it, okay? So with that, if you think about, the barriers, if I have what? If I have electron goes from here to there, that barriers, right? That barrier is reduced by this delta EC, right? So initially, see the difference here is QVBI, right? You have what? QVBI minus what? Minus delta EC. That's the barrier, how much barrier reduced by delta EC. But on the bottom, you see here, that will be what? Plus QVBI. You see here. Now for the hole, if this hole tries to go down there, the barrier has been increased by their delta EV, okay? So the offset, between the N and P for heterojunction, they can either reduce the barriers for electron or hole while increase the barriers for the other one. Or they can reduce the barrier for both, right? Okay. That's what you see there. And then you can use this to calculate, what delta EC, right? Delta EC basically equal what? The electron affinity on the P side minus the electron affinity on what? On the N side, because that's basically how far this EC away from the vacuum level, right? That's why you use that minus each other, right? Delta EV will be, the band gap. You see the band gap here. This is the total band gap, and then, the band gap, then minus the band gap on this side, right? And then you minus delta EC, what do you get delta EV, right? Because this plus that equal to what? If the left band gap, okay? So with that way, you load delta EC, you load delta EV, and then you can calculate the QVBI, right? QVBI probably easy. Basically EF1. Right, see here, this EFP minus what? EFN, right? EFN. Okay, EFP minus EFN. What is EFP, right? EFP basically what? This electron affinity plus the band gap, and then subtract what? Subtract this, right? Is the total here, and then minus the here. That's what you see is there. Okay. The same thing. EFN. EFN will be what? The EC plus what? Plus look here. EC plus the difference there. That difference. Okay. That's the difference. Okay. So here you can see, you can with these band structures, right? You will know how the banding look like, and then what is the barriers, for positive charge, what is barrier for negative charge, and then you need to plot this. You will know what's going on. Okay. So that's what is this about, and then. So with that, in order for you to understand the junction, right? To understand the junction, now let's see, right? I just talked about that, right? So the barriers, if there's your homojunction, the barrier is what? Is about 1.07, right? Now since the delta EC here, for these things up, you kind of reduce that barrier by 0.25, right? That delta EC, if you see here, you calculate that, it's 0.25, okay? Delta EV is 0.43, okay? The VBI is 1.07. I'm sorry, 1.07, yeah, EV, okay? So that's equal to 0.25, right? 0.25. This equal to what? 0.4 what? That 0.43, okay? 0.43, okay? 0.43, 0.5. And then what do you see here? This one will be total equal to what? Total is 1.07 minus 0.25, right? So that barrier is what? Is 0.82 EV, okay? For electron, right? For electron, okay? And then for hole, For hole, then you have what? You have that 1.05 plus what? 0.43. You have 1.5 EV, right? See, the whole barrel become bigger, and then electron barrel become what? Shorter. So this, the offset at this EC conduction band actually reduce what? The barrel for electron, but increase the barrel for hole. That's what you see. Okay. You can also see the electrons are more favorable than holes. Okay, to pass through the junction. Okay. So that's about that. Okay, the same thing here. I think you guys can plot it by yourself, right? Very similar, right? Very similar as I just showed you there. Now if this band structured like this, P type, alpha silicon, that's amorphous silicon, right? And the N type, crystalline silicon, and then the electron affinity is 3.8 for amorphous silicon, and then how far that Feynman average is above the Valence band. That is about 0.1, right? That's 0.1. This is equal to 0.1. Okay, 0.1 EV. Okay, then the band gap for this, what? 1.8 EV, right? And then the same thing here. You see the total band gap. What? The band gap. Okay, band gap there to here. That's 1.12 EV. 1.12 EV. Then the offset here, you see here, equal to 0.2. Okay, 0.2 EV. That's equal to 0.2 EV. Here is 0.2 EV. 0.2 EV. Okay. And then this one is 4.05. This is 3.8. Now, if you plot this, you can plot it by yourself, right? Basically, what you do, you keep the left side the same, and then the move right side down. This guy goes to here, right? This guy goes to there, and then on the far away from the junction, this stays the same. This that you call that delta, right? That delta n will be stay the same, right? That delta n stays the same. You see here, it's 0.2 EV, okay? And then this guy also stays the same. That's what. See here, this is 1.2, 1.12, that's 0.2. So here is 0.92, right? This is 0.92, okay? 0.92, okay? 0.92 EV, okay? A total add together 1.12 EV. And then on the left side, what you see here, initially it should be collected together, right? But if you know the junction, the interface is happened here. No, the interface, right, is happened here. And then what you see, because you offset here, on left side, left side is higher than right side, right? How much difference? That's equal to 4.05 minus 3.8. That's equal to what? 0.25 EV, okay? 0.25. That's delta EC, okay? Delta EC equal to 0.25 EV, okay? And then look at here, how much distance you have, right? You can calculate what? This total is 1. Okay, at this 3.8 plus 1.8 is what, right? That's 5.6, right? 5.6, right? 5.6 minus here. So this guy 4.05 plus 1.12 is what? That is 5.17, right? 5.17. Get this 0.33 EV, right? That's it, right? That's 0.43, right? 0.43, okay? That's 0.43 EV, okay? Not point. That's 0.43 EV, okay? And then that's delta EV equal to 0.43, okay? 0.43 EV, okay? And then what you see here now, since this side on the right side is taller than the bottom side, you see here is 0.43 EV. And then for the delta EC, since the left side is taller than here, you see that what? 0.25 EV, okay? Now you can do the same thing, right? Apparently for electron, now the barrel get higher. How high is what? You add 0.25, right? For hole, the barrel gets smaller because you're offset, right? You need minus that 0.43, right? That's why. And then you can also calculate what? You can calculate QVBI equal to what? QVBI equal to what? Basically, you can see here is what? Look at here, 5.6, right? This one 5.6, then this one is what? 5.5, right? 5.5 EV. And then see here, this total is what? 4.05, right? 4.05 plus this 0.2, 4.25, right? This one is 4.25. 4.25 is here. This is what? 5.5. So that's Q what? That's its Q VBI is what? It's 5.5 minus what? Minus 4.25. That's 1.25, right? 1.25. See here, this is 1.25. Okay. That's 1.25 EV. Now you see, QVBI is 1.25 EV. Delta EV is 0.43. Delta E what? Delta EC is what? 0.25, right? And then basically this barriers become what? This plus 1.25 equal to 1.5 EV. This one is what? 1.25 minus 0.46. That's equal to 0.8 what? 2 EV, right? You see, now on the electron, the barrier reduce, right? And then the hole, the barrier increases. Okay, that's what it is. That's what it is. Okay, so this is here's an example. Basically show that if you know this is a point 0.5 EV, right? This 0.5 EV, and then the barrier will be reduced, right? But for electron, if the holes go this one, see something like this. See here is EV, right? EV. So for hole one, it's a high barrier for hole to transport from P to N, right? And then not higher, it's lower, right? If there's no such things there, the barrier is 1 EV, right? Electron goes, the hole goes down, it's more difficult, right? Hole goes from what? P to N, it's more difficult. Now, since you push this up by 0.5, the total is 0.5 EV, the barrier now is 0.5 compared to 1 before. So electron goes from what? From P to N. It's easier, okay? That's basically reduce the whole transport resistance or whole transport impedance, okay? That's it, okay? That's about that. And then next thing what we try to discuss is called, space charge regions or approximation, okay? That's basically, if this is my N-type materials, this is my N-type, okay? Why is N-type? Because Fibonacci is close what? Close my EC, right? And then, get close to junction. If my junction is here, if the band bending goes up, the delta phi. Now you can calculate in these positions, right? In these positions, basically you have what? You have ionized ions, right? Since this N-type, you have ionized phosphorus, right? That's Nd, right? You have ionized Nd, right? That's positive charge, okay? Positive charge. See here? That's the positive charge. Plus. And then the P9 is what? Also positive charge. That's basically the minority carriers in the N-type, right? That's positive charge. And then you have electric charge. That's what? That's majority carrier, right? That's N9, right? N9 is majority carrier, okay? Now what you see here, since at these positions, think about these positions, the whole like the flow there, right? So that is, if my minority is what? Ni square over Nd, right? You know that, right? My N9 P9 equal to Ni square, right? My Ni square, right? So my N9 is equal to Nd, right? N is Nd, okay? That's why my P9 will be what? Ni square over Nd. See, this is my P9. This is my P9, right? My P9 is here. Now goes to top. The whole like to flow to the top, right? That's why exponential positive delta phi over Kt, okay? That's the total thing about what? That's the P9, okay? And then the Nd here is still the total, carrier concentration. That's the dopant concentration, right? And then if you look at this N9 will be what? N9, since here's Nd, see here's Nd. Now, energy goes top. When it goes top, electron will reduce their concentration, right? That's why exponential, this is negative, okay? This is negative. So what's here, this is the P9, this is Nd, this is the N9, okay? And then add together, that's almost close to QND. So QND, because you can take a QND out, look at this equation. You just take a QND out, okay? Take a QND, get QND out. This one Ni square of Nd here. And then this 1 minus that, the delta phi is delta phi get what? Get to farther away from here, you know, this is big lective, right? So this guy will be cancer, right? So something here, since Ni is what, 10 power 10, Nd is 10 power what, 15? See how like 100,000 bigger, and then the 100,000 bigger, you know, double, right? Squared, and then you hit what? Just like a 100,000 times 100,000, right? That's huge, right? That's about 100 million, right? 100 billion. That's why, you know, cancel this, what remaining only one, that's why it's equal to 20. Okay, 20. So that's to analyze the N-type. If you analyze the whole, the P-type, you get almost the same thing, right? You think about the P-type, the band is here, find these positions. You also have what? You have this, now P-type, right? Majority carrier is P9, right? And the minority carrier is elective, right? Electrons. And also all the what? All these ionized ions, right? That ionized ions is what? Is negative because this P-type, you have free electrons that's positive. Now you lost that free positive holes. You lost a positive holes. Now the only thing is negative ions left. Okay, that's why this negative ions. Okay, that's selective. Okay, negative ions. And then I can do the same thing. That's Na is negative ions, stays the same. And the N9 because of what? N9, right? N9 is here, right? N9 is here. Now N9 goes down, right? N9 goes down here. This is N9, right? N9 equal to 10 power 4, right? And then now goes down. That's why N9 what? Will be multiply the positive delta phi over KT. And then for whole P9 goes down here. Whole cannot go down. So that's why it's negative, right? Negative. Now with this, you can take QNA out. The same thing here, right? Same thing here. This side is the, you know, this is a, you know, delta phi over KT. That's negative. So this is small, right? And times here, Ni is so smaller than Na squared, so this gets gone. So the remaining will be minus 1 times that's minus QNA. Okay, minus QNA. Okay. That's about how you analyze this. And then if you look at this p-n junctions diode, you know, they have the similar things as we discussed before, right? You also have what? P-type, right? And they have N-type. Okay, P-type, N-type. And then, you know, in the junction here, P-type, you have all the positive charges gone. You have negative ions, right? Negative ions, right? And then on N side, you have positive ions, right? Positive ions, okay? That's the positive ions, okay? Now you see, since the positive ions, you have a higher concentration, right? If the N-type is highly doped, P-type is normally doped, you have more charge carriers. The charge carriers, you know, may be bigger on the right side. That's why it's wider, okay? But that may not mean it's bigger, just say it's wider, okay? And then you get with this rho, right? Rho over epsilon, right? Is equal to what? The rho will be equal to this guy, right? So QD over epsilon. This one, you know, this is N, right? Epsilon N. Then the other rho here will be what? Rho over epsilon what? P, right? Now, since the P and N are different materials, so that what? Because one is amorphous, one is crystalline. So epsilon N is not equal to epsilon, okay, epsilon P. Okay, that's it. Okay. Now, if you do integration of this, you know, do integration of this, something here, then you will see, to integration of this left one, you get something like this. Integrate on the right side, you see something like this, because left one you have this, you know, epsilon P, right one epsilon N. Now that's why they are different, right? Even the charge is the same. QNA XP is equal to what? Look at this. QNA XP equal to what? Q XPNA, right? Q, you know, XN and D equal to Q XPNA. But now since they divide by epsilon, N, right? Now since this and this are not equal, right? So that's why, you know, what you see here when you do the integration, you see gap there. You see the gap because this one is not equal to that one anymore. Even this guy is equal to him. But since they divide by the dielectric constant, the dielectric constant are not the same. That's why you see gap. You see this much gap, okay? One here, one there, okay? So the other way you can also see that's something called what? Electric displacement, okay? Electric displacement is the same. but electric displacement is equal to the epsilon multiplied the electric field, right? Since this d1, d2 is the same, but epsilon I is not equal to what? Epsilon 2, that's why the electric field is not the same. That's why you see one is here, the other one is here, okay? That's what is that, okay? And then since now you know the electric field distribution, something like this, and then if you do the integration of this, you'll find out what? You will find out the integration of left side, integration of the right side. Since this is a linear, so here is get parabolic, right? Okay, here is parabolic, okay? Parabolic. One parabolic here, one parabolic here, right? Now, since the electric field here is not continuous, this position may not continue. That's why you see something either like this or like this. You see they're not continuous. They're not continuous. Okay, that's the same concept if you do integration. Since integration, that electric field is not the same because you do the electric field into you do what? Electric field integration, you get the V, right? You get the E of V. That's the same thing. Okay, E. That's it. That's what you see here, right? This electric field, on the P side, this on the N side, and then if do integration of this, what you see here, either you get JP on the P side, and then you can also get GIAN on the N side, okay? And then these two may not continuous, right? They may not continuous. They can be displaced, okay? That's what you see. Eventually, you see GM plus GP. That's called VBI. Okay, that's VBI. Okay, this is the real VBI. But that VBI doesn't mean at that HOMO level or Newman level or conduction band, valence bands have the same thing. Okay, and then with that you can summarize this. This is what the p-n junction and heterojunctions. The only difference you compare to the homojunctions, you see here epsilon is the same, right? Epsilon is the same. That's why no epsilon here, right? Right. But now, since this heterojunction, right, you have p side, you have epsilon dielectrons, and n side have dielectrons, and they're not the same. That's why you have to include this, in the period potential, and then you add these two together. That's what you see here. Y has n side dielectric constant multiply nd plus p side dielectric constant multiply what Na, and then that would say Gp and then get Gn. You add these two together, that would be total, barriers you will see inside the p-n junction. So basically the same thing, right? If you can find out xn, xp, the W is xnp, and then you can find a function what for VBI, right? For VBI, okay. But basically, if you know this, right? If you know this, right, the materials you know this, that you can find the VJP, VGN, they add together be what? The VBI, okay. That would be also a function of what? The XP and XN, okay. That the comparison of homojunction is much more simpler, okay. Simpler, okay. That's it, okay. And then I think we talk about the band energy diagram for matter semiconductors. So matter semiconductors, I think we did this before, right? I'm not going to repeat this, okay? I'm not going to repeat this, but what you can see there, this is the matter, right? And then these are semiconductors. Something like this, you need to move this one down, right? Move this one down, and then the same thing there is here, right? And then this guy will be moved the same distance down. That will be here, right? It will be here, okay? So you see this is junction, okay? This is where your EF, right? This EF, okay? And then what you see here, since what? At these positions, this EC is that much above what? Matter. That stays there, right? That's a stays there, okay? That's what you see here. That's what you see. And then the same thing here. This one, this one at the junction is that much below that. That much below that. That stays there. So that's what you see. Okay, you see here, right? You see that? Yeah. If you collect them together, it's something like this, right? Together, this one. Okay, that's how you plot the matter semiconductor junction. Okay, you can plot it by yourself, and then you'll be able to calculate what? Calculate the QVBI, right? That QVBI is equal to, the phi m minus phi x, okay? Phi x. That's basically is this distance, right? Minus what? Minus this distance, right? And then also actually is the Q. Okay, I think this is here. Okay, let me erase everything here. This is too much things here. It's so confusing. Okay. everything here, okay? And then in order to find the, QVBI is the building potential. That's only the difference between the matter work function and then what, Feynman average, right? That's basically this distance. That's why if you get this distance, minus what? Minus this guy, and then minus again, minus this guy. Yeah, that's what you see here. Then you get that 1.4 EV, okay? 1.4 EV, okay? So now you know that the matter semiconductor interface or at matter semiconductor junctions, you also get what? You also get the barriers, right? The barriers about 1.4 EV, okay? And then with that, actually you can also do what? You can also calculate this, right? You calculate from this, you know what? You know the metal here, right? This metal. And on the right side, you have semiconductors, right? Semiconductors, okay? Semiconductors. Now what you see here is what? Since there's band bending here, right? The band bending here, right? And then you also know in the depletion regions, right? Depletion regions, right? What has been depleted, right? Since here is what? Here is N-type, right? N-type. So negative charge depleted, whatever is still is what? Positive ions, right? Positive ions stay in this region, okay? That's positive ions, right? That's why if you look at the charge in these regions, because I say W there, you can make it W secret, right? Here to be aligned with this, W is where? W is here, right? W is here. Right, that's W. So that means all this positive charge, right? Just assume everything inside the N is what? Is depleted, right? We have only the positive ions inside. This will be the positive ions, okay? That's why it's positive, right? Because the positive ion, that's how the charge you see there, right? And then on the interface, suddenly you see a lot of what? Negative charge there, right? Negative charge at this interface. Because the metal, right? The metal cannot hold the metal has a lot of electrons. You cannot hold the hole inside. That's why it's recommended, by the way. So that hole still what? On the interface, right? On the interface. Now what you see? Suddenly there's a lot of hole at the metal interface surface, and then on the right side there's a lot of positive charge there. Okay, and then you do integration of this, right? You know the area Q and D multiply W. That's here, right? See this one, Q and D, W, and then divided by what? Divided by the semiconductor, right? N-type semiconductor dielectric constant, right? That's what you see here. That E. If you do that electric field integration, from here to there, right? Here you see significant what? Electric field, and then get to the edge of this depletion regions is zero, right? It gets to zero. Electric field is gone. That's why you do integration from here to there. There's a linear, right? The kx integration will be kx squared, right? Plus bx or something. That's why it's close to parabolic. Okay, parabolic. Okay, parabolic. It's here. Okay, parabolic. And then with that, you can calculate VBI, right? VBI basically equal to Q and D W squared over 2 epsilon m, right? And also the VBI can be calculated from what? The phi m minus phi s, if you know the band structure, okay? So, you use this one. You know that if you can find what? If you can find, this is something we discussed before, right? You can find the carrier density, right? Charge density, you do integration of this, you get E, right? Electric field. And to the electric field E, you get what? Get this V potential, or you get QV, right? That's either way, right? Typically, electric field itself is get V, the potential, and then you multiply Q, you get that energy rate, okay? Energy level. With that, I think we already talked about this, right? You see, this is the special charge regions. The metal is here. This N-type, that's why, get this electric field distribution. Then do electric field, it's linear kx. That's why when you do integration is negative. So that's why it go parabolic like this, right? Then that's what you see here. This one, whatever here, is the same thing as here. Okay? That's why the bending happens as a parabolic, right? Parabolic, okay? That's just because that's in the junction, That's in the junction. That's in the junction in these regions. Right? That's the same thing, okay? So exactly it's the same concept. And you'll be able to calculate VBI equal to GN because now you don't have GP, right? That's equal to this. Similar to what? Similar to here, right? That's just integration of this guy, right? That's basically the area. Half of this multiply that, right? This divided by that get half, right? And then you take half of that. The same thing here, right? Something here, half. I multiply xn, right? W, right? The W is xn. Okay. That's what you see, and then you can calculate xn is this much. That tell you for the metal semiconductor, in phase, what is the depletion region? How wide is depletion? Okay. So this about the heterojunction. Okay. I think we can continue to next chapter. Okay. Let's continue the next chapter. Okay. I'm going to leave this here in case someone has questions. Okay. And then we'll talk about the chapter 5 line. Okay, chapter 9, we're going to talk about thin film solar cells. I mean, this chapter 8 is also thin film solar cells, but chapter 9 is the more thinner film, right? Film can be thinner. And then we call this third generation solar cells, okay? So these thin film solar cells, basically, if you look at that, let's just compare, damper, right? Crystalline silicon solar cells, you have single crystalline, the fourth generation, you have what? You have 300 micrometers. Right? And earlier, before this chapter 8, we talk about heterojunction, right? Heterojunction is also we involve a lot of thin film solar cells. But now, we'll try to reduce that, thickness from 300 micrometers to 1 micrometers. Okay. Then typically the thin film solar cells shows high potential, for cost effective because it's cheaper. The materials is cheaper, right? And it's not like a silicon, you have to grow the single crystals, right? And then there are many different technologies, right? You can see a CVD, sputter systems, co-evaporations. All these can be used to prepare thin film solar cells. Okay. And you can also, modify the materials, tune their band gap. You make the multi-junction solar cells. Okay, that's the other thing you can make. So basically, with the thin film solar cells, you have, more access, more flexibility to get new materials, and then you can also deposit your different substrate like a glass, stainless steel, or plastic to fabricate the solar cells. And also, if you think about organic solar cells, perovskite solar cells, Dyson-side solar cells, these are all, third generation thin film solar cells. Okay, so that's about thin film solar cells. So basically, thin film solar cells, they have lower quality, semiconductors, right? And then also, you can synthesize the lower temperature, right? Because you don't need, single crystalline materials. That's why you use, amorphous materials, polycrystalline, multicrystalline, nanocrystalline. Okay, that's why the materials property can be quality get lower. Okay, and then the deposition, as I just mentioned, you different, many different depositions instead of diffusion, right? That's what's used in silicon solar cells. So since now your property or the quality of the fumes is lower than the crystalline silicon. So that's why the efficiency of thin film solar cells is lower. Okay. So with that, you can see here are a bunch of materials here. You can see, polycrystalline silicon, the band gap is about 1.2 eV, right? Amorphous silicon is 1.7 to 1.8 eV, and then multicrystalline silicon or nanocrystalline silicon 1.4. Now you can see, right? You can see that, right? Even the same silicon, you can make them amorphous, make them multicrystalline, and you can tune their band gap, right? Okay. So with that, you see high efficiency, thin film 3.5 solar cells. Then you can see, gallium nitride about 1.4, and then gadolinium phosphide is 1.8, and then many others here. You can tune the band gap. That's the beauty from you make the materials for different processing, and they can tune their band gap, depends what the band gap we are looking for. So here shows more, so typically CIS or CIGS, CGS or CIS. Right? This is the band gap can be tuned from 1 to 1.5, 1.7, right? And also, you can use tandem telluride, right? You get 1.45 eV, okay? So, and then,
Professor,
yes.
Professor, sorry to interrupt you, sir, but slides are not visible. So have you shared it? Cannot see your slides.
Okay, maybe, okay. I'm sorry. Maybe I forgot to share. Okay.
Okay, sir.
Yeah. Okay. Sorry about that. Okay. With that, let me go back a little bit, right? So the next time if you see this, maybe tell me from the beginning, okay? Because I just stopped the other share slides and then apologize for that, okay? Forgot this one. Okay. So this one I'm talking about, uh, different depositions, right? Thickness get reduced, okay? The efficiency will be lower, but can be more cost effective because it's cheaper, and then you can use different substrate. That's what we discussed, right? And then, thin film solar cells, become flexible solar cells, this is a key point, right? The materials has lower quality, right? Because now you don't use high temperature, right? That's why you have what? Polycrystalline, monocrystalline, nanocrystalline, amorphous, right? Then also because the material quality is low, you can use lower temperature, right? Process. That's why the processing can be cheaper, okay? And then you use different depositions, right? That's instead of what? Instead of diffusion process, right? Overall, the efficiency will be lower because the material quality is much lower, right? That's what I was just discussed, right? And then here shows a bunch of different materials, right? The silicon, you can have what? Polycrystalline silicon, amorphous silicon, efficiency 1. Not efficient, the band gap 1.1. If you use amorphous silicon, 1.7, right? 1.8. Polycrystalline or not polycrystalline, multicrystalline or nanocrystalline, you get 1.4 to 2. That's basically you can tune the band gap. And then there's a bunch of different semiconductors, 3.5, See the band gap can be different, right? They depend on your need. You can tune the band gap easily. Right? And the same thing, more materials here, right? You tune the band gap, right? And then, you know, many of these will be the direct band gap materials. That's why you can do thin film, right? Whenever you use thin film, the materials has to be direct band gap because you want to have a higher absorption coefficient, right? And then, nowadays people work on the what, like a newer, the next generation, like organic solar cells, these polymer dyes, all these are what, direct band gap materials. And then new type of solar cells will perovskite solar cells, okay? And then, that's what we that's more like introduction, what is third generation. And then since we talk about you can use different deposition method, right? You can use sputter system, chemical vapor deposition, cold vibration, and then that's basically depends the method you're using, right? You can get the defect easily. Okay, you can get the defect easily. So typically, if you use, sputter system, maybe many of you, right? I believe many of you are either PhD or master students. You do a lot of depositions in your lab, right? If you use sputter system to make, the silicon germanium or gallium arsenide, you will produce a lot of defect, right? That's typically what we found, okay? What the literature see, right? And then if you use sputtering to make what? This carbon telluride, CIGS, zinc oxide, tin oxide, and then you see the defect only happens that close to what? The conductor band or valence band, that's called shallow defect, okay? But if you make sputter the silicon, this germanium and the gallium arsenide, you will generate the defect almost everywhere, okay, everywhere, okay? So that's what we discussed. And then since we talk about, crystalline silicon, polycrystalline silicon, multicrystalline silicon, then we also talk about what? Amorphous silicon. Then you can see here, right? So basically, why we call that single crystalline, basically the entire, wafer or ingot are single crystals, right? And then multicrystalline silicon, that means what? You have some part is the multicrystalline, or these, say shiny regions or dark regions. These are what? The crystalline materials. But they are not continuous, right? But outside there, they have a lot of what? Dangling bonds, there's, surface, and then that's why they look different, right? And then polycrystalline is the same. Now the size of the crystal reduced to what? 1 micrometers or few micrometers. Now multicrystalline, you can see that can be, hundreds of micrometers or even millimeters, right? And then you further reduce that crystal size, from 1 micrometer to what? To nanometers, you call that, nanocrystalline or microcrystalline. So that's basically, depends of the size of the crystals you have in your sample. And then you can see they are either what? They are either, single crystalline, polycrystalline, multicrystalline. this kind of thing. Okay, so that's is about that. So next thing we're going to discuss will be what? Let's think about single junction, right? Especially for thin film solar cells, right? If you compare this with conventional silicon solar cells, typically you have this. You remember you have the emitter there. That's enough, right? You don't need this TCO, right? But the thin film solar cells, since their quality is that high, right? You cannot deposit really high quality materials. That means the electroconductivity is not that high, right? That's why you have to deposit transparent conductive oxide, the TCO there, right? Basically, you put TCO there, and then underneath that, you can either use window layer, you use the emitter layer, that can be P plus or N plus, and then under that, you typically have this NPOI layer, right? Then that's how you make this solar cell work, right? Then sometimes people also, for the back contact, they add what? They add window layer as well, right? Depends. That depends what you. Okay. Now, if you look at these examples, which phonic structure is the best to reduce the loss in silicon solar cells? So the answer here would be A, right? It would be A. But actually, you will select A and B the same, similar sense. The only thing we say A because typically the hole has what? Hole has lower, right? Has lower mobility. That's why the light will be absorbed most on the top regions, right? And then you generate the hole, right? The hole can easily get to what? P plus and then get to TCO, right? If the hole stays here and then the pass all the way there, it's difficult, right? So that's why we want holes to absorb force. But that's a theory. But in practically, you can either use N B the same, okay? N B would be. So if you look at these questions, basically ask you, if there's a TCO here, right, and then there's P plus. If you see there's some charge, some charge like the hole goes to here. Now there's 1, 2, 3, 4 different possibilities for the hole to transport, right? Since the TCO, right, that's the called transparent conductor, it has very high conductivity, right? So when the electron hole gets there, it's transported immediately, right? So that's typically like a highway, right? Like if you drive, right, you like to get to highway as soon as possible, right? So that's why the 4 different channels, number 3 will be most efficient. Electron like to get to the highway first and then move to the contact. They don't like to stay in the P plus a long time. All you go, typically this one you will find one closer here, right? You don't want to like to go there, you don't go all the way to the other contact because you are closer to this contact, right? So with that, you see the answer here is what? Answer here is basically it's a 3, right? Pathway 3 will be what typically a hole like to transport, okay? So here's another diagram shows the GIAN solar cells, GIAN solar cells, that's basically you see the sunlight comes and then basically ask you why the P layer is right below this. I think I just talked about that. See, why the P layer is here instead of N plus? Okay, it's instead of N plus. Reason there basically is what? It's actually because the majority of the sunlight, will absorb as the top layer. Get closer to here, right? Okay. When you generate electron hole, right? Because the electron has what? Very good, very high mobility, can transport a long distance. That's why you want the electron go all the way down. You want the hole goes up because hole is, has slower, mobility. That's why you want it to go up, right? Because that distance is shorter for him. Okay, that's why the answer here will be ABC. Okay, I'm just trying to give you a very quick, concept here, and you can read the question and figure out this by yourself. Okay. That's about that. I think here actually explains what's going on, right? Explain why the hole goes so top because the hole has a lower mobility, right? Hole mobility typically, if you think about hole is about 0.01, the electron mobility can be 100 times bigger, okay? Especially for thin film materials. So that's why, okay. And then the next thing what you see will be the band gap. You know, you may ask questions, especially in the beginning, right? We talk about what band gap is the best, right? Then you'll see the band gap can be changed from 0.8, 0.5 to what? To 0.5. And the best band gap, single junction about 1.45 EV, right? 1.45 EV give you the highest efficiency. Why is that? Because if you look at that, if you think about this is silicon, right? Silicon has absorption to here, right? to here, because silicon band gap is by 1.1 eV. That means the cutoff wavelength will be what? Be by 1100 nanometers, right? And then even silicon can absorb a lot. Look at the silicon, right? Your silicon can absorb more all this, right? Silicon absorb all the light to here, right? To here. But unfortunately, you cannot convert all that, photon energy into electricity because what? Because you have solmonization loss, right? The solmonization loss will be carried, cured this much, right? That's part here, okay. See all the loss here, this one. This called solmonization loss. Why? Think about this, okay? Your silicon has a band gap 1.12 E. 1.12 E. Now there's a 2.24 eV photons coming. Then the electron promote to there, right? To there. And then you see there's solmonizations, electron. So eventually, how much energy you get, right, from that photon? That's 1.12 eV. The other 1.12 eV, it just becomes solmonization, right? Become hot, right? Solar energy inside the material. Your material get heat up, right? That's why the what? That's why the your band gap is important. You don't want to use very small band gap because you will have a lot of solmonization loss. But you don't want to use very high band gap because you will not be able to absorb what? Enough sunlight, right? That's why if you think about, the efficiency equal to V times I, right? That will be basically the band gap, right? The band gap, right? Band gap multiplied by I. When the band gap is what? The band gap is high, your I is small. When the band gap is small, I is bigger. That's why the band gap multiplied I has to have some maximum at some point. So, by instance, that happens about 1.45. Okay, you can do the simulation here, right? You can EG, right? Because the real energy, no matter how big your photon energy, when your photon has energy higher than band gap, you only can convert that band gap energy and then multiply how many photons you have. But the efficiency is divided by the total photon energy. That's why this E is inside the integration. Here is the E outside integration. Okay, if you use this, you'll be able to find out that 1.45 is the highest. Okay, it's the highest. And then, so here's another slides shows that, I think this is something about heterojunction. We talked about this before. Right? We discussed that before. Here we basically show your equation, right? The equation for the heterojunctions, right? We also have this, these equations when we talk about, homojunctions. We got the same thing, right? The only difference, we use this one in the homojunction. We don't have this, right? Now, since what? Since you have this guy, you have since either like this or either like this. You see that the pairs either for electron or hole will be different, right? So that will determine, whether inside the junction you have in junction, if you go from here to there, you call that emissions. Then outside the junction, you call that diffusion, right? This one is P because the P side, right? dP, the diffusion P side. This one will be D what? V dN, right? Because the diffusion on the N side, right? So now since this delta EC, delta EV affect this what? EMS. And then now EMS will be compared with, diffusion, right? So basically inside the junction, that will be different from the homojunction because what? Because now you have delta EC or delta EV, right? And then that compares the depletion regions, right? That's why you have this portion, right? You have this portion. This portion, okay? This portion, finally you'll get, I'm gonna skip this. You can think about this by yourself. If you have a question, I can answer, right? Basically, you can find, this is something we discussed before, right? See here, this is the minus, and then this get higher, right? If plus, this get lower, right? It's the same thing. This side will be the same thing, okay? Then what you have this is what? This more like dark current, right? Dark current, and then multiply this part, tell you which one dominant, right? Which one dominant, and then multiply this normal one, the direct current, right? Then you can see there, if you multiply this, right? Because NISP square, NIP square, you can find what? Yeah, that's the same thing. Okay, maybe what you can do here, right? Here, and the GN, right? GN equal to Q delta N, right? And then delta N V, right? V, right? Delta N is that delta N, and then V will be what? V will be the VDP, right? Because this one is a direct, right? Direct one. That V is the velocity, right? That's velocity on what? Depletion region, right? That's why this one, if this guy multiply VDP, what do you get? 1 over VDP plus 1 over EMS, right? Then with that, now if this VDP is much smaller than here, if the VDP is much smaller than this one, then that's heat dominant, right? Small one, this one big, right? Then if VDP is bigger than that, heat dominant, right? That's why smaller one dominant, right? Smaller one dominant, okay? So that depends, right? Depends whether this delta EC or delta EV affect the EMS, and then that will be because VDP will not change, but if EMS change, then that determines what the junction look like. Okay. So the same thing here. This one is basically what for the P side, and then if you do the N side, you get the same thing, right? VDP. Okay. So okay, I'm sorry. This one basically talk about I think EV, right? This also EC. Okay. This is the minus EC. See, this one is minus EC because it goes that EC reduce. Here is a positive EC, right? That's the positive. This is positive. Right? This shows the difference here. Okay. Difference. Okay. That's basically the same thing. You just find the difference. Okay. With that, I think we have 2 minutes, right? Probably. I think we can leave this. We have about 10 slides. We'll go together with what? With Friday evening, right? Friday evening, my time, your time, probably Saturday, right? Saturday? Yeah, Saturday morning, okay? I'm going to talk about the remaining 2.5 chapters, okay? The remaining chapter will be really not that difficult. It's more like concept, okay? With that, I think we can stop here at this moment, okay? This slide 24th, right? I'm going to remember this, okay? Probably another 10 slides, and then 2 more chapters will be finished this. So now any questions? We can have 1 or 2 minutes, take 1 or 2 questions here, okay?
Thank you, sir. Participants, you can raise your hand now if you have any question.
Okay, if no question, I think tomorrow, right? We still have some time to answer questions.
Yes, sir. Maybe we can take them later, but for now, I guess we don't have any question.
Okay, great.
Yes, we can close this session.
Okay, thank you.
Thank you, sir. Thank you.
Yeah, we'll see you this evening, right? You guys' time. Okay.
Yes,
bye-bye. Yeah.
yes. Bye. Thank you, sir.